So the last lecture, it's everybody sleepy. I'm sleepy too. So I won't go too far. We're just doing some linear algebra. So I will talk something about ideal proof. If we still have some time left, I mean, there's no limit anymore. So we can talk something, the local Gross-Zagier formula. So basically, this is the crook of the matter of the whole business. It's kind of analog of the trace formula, or if you want to think it, the more philosophical way, the fundamental lemma between two different worlds. So there's a representation, geometry, whatever, the whole the combinatorics been put in this lemma. The proof, I just want to state the proof of 4 steps. Step 1, so I will only, so for simplicity, it doesn't matter that we only think about the order case at the very beginning, but this is not really, well, I'm just forget about it. So construct, so for the order case, so construct a form phi of level ND such that the derivative 1 chi f is given by the inner product phi f big phi ND. So this ND means that you calculate x naught of ND. So now you ask me why you directly compute something with a level n. So natural thing should be done at n. Well, the difficulty is that the Rankin-Selberg method, you start with has something the theta series involved. The level of theta series has a level d. If you insist to do it at the level n, then what you need to do, you need to take the trace. Now this will be the level n. The problem is that this is very difficult to compute. If this is a trace, if d is not square free. And this first remark. Second remark is more silly. I mean that you think the form, the new form. If I define a new form somehow, if I later on when you linearize this right hand, you can linearize this thing. It become a functional, the space of n. Then you think of this as a functional, f prime 1 chi f. Then it's a linear functional. This is a finite dimensional space. So anyway, it's represented by a kernel. So existence of a kernel is not a problem at all. But the problem is the construct. Construct means that you understand the Fourier coefficient, everything. Since this is a level ND instead of n, then what's going on is that, so let pi over phi be the subspace, is the space of automorphic forms of forms generated by f, I mean that and the Heck operators. So I mean Heck operator, not so much Heck operators of TV for V not divide for V divided D. The reason is my f has let me say this is silly. So Heck operator is something of this thing. So this is f of this G of A 0, 0, 1. For example, write this one, the f of A. So in other words, it's generated by all these FAs. And, or maybe something else. Let me write down something more precisely. So this is really a space of rho of G of F, the combination of this thing, and the rho H, F of G equals F G H. So you get this space. This is kind of a representation. This is kind of a representation given by G of AF, A, or doesn't matter, PGL2. Now what's going on is that this phi will have a projection. In this space, pi of F. And since the level I put here is not exactly n, you don't expect that the projection is a multiple of F itself. So this projection actually is a summation of some C of A, F of A. So I just write down this F of A, G is just the F of G, A inverse 0, 0, 1 for this A divided D. So this, in other words, is some new form plus some older form. And that's the standard thing you will get. So the projection formula is given by the following. So the projection of this phi and space pi of F is nothing else. Is a form, I can write down, is derivative 1/2 of chi phi divided by the norm phi sharp square. I will describe what the phi sharp is. So this phi sharp is some linear combination CA. I have to write everything in the F. CAF of A, and it is characterized by the following property: F sharp, FA. The inner product is given by explicit formula chi of B. This chi is a quadratic character times F sharp, another was 0. So if this B, if A divide the discriminant K of F, and the B is a norm from K to F, is a norm, is generate the same idea as A. So inside A times OK cross, AF cross. So recall that my chi is unramified character at every place where K is ramified. So it does make sense to define the chi of B here. So this is determined. So I call the name F. This one is called a quasi new form. Well, so there's already a problem here. So instead of work on new form, we work on a quasi new form. This is step 1. So when you work on an automatic form, that's always the case. You can't just work on a new form all the time. So step 2, well, we construct another modular form. A form, big phi, I don't know, big psi, that is the psi, whose Fourier coefficient, when I call Fourier coefficient, it means that we are in where 2 case. So the weighted function at the equivalent place is fixed. What's left is the Fourier coefficient. Fourier coefficient is given by something like that, T of A, Y chi sharp, Y chi sharp. So this is Fourier coefficient. What?
Wasn't there 1.5?
No one. Oh, yeah, the 1 here. So I always skipped from the center of symmetry here is 1. So this y chi here again is a chi quasi-Hington point. So why is the quasi-Hington? It lives in different Shimura curve. I'm trying to describe it. It's not really that hard to describe. It's different than the Hington point I described in this morning. Namely, I still have this b x quasi x sharp is something g of f positive h dot g of af, and this one is some r sharp. So this r is that this r sharp can be written down as OK plus C of chi OK times something lambda. Okay, I mean that everything is right locally. So the lambda v, of course, x equal x bar lambda v. The norm of lambda v equals n v. So this is the order completely, I mean, it's really strictly 2 components. It's quite different than the norm I get. So now a CM point is the y chi sharp is the summation Let me see how can I explain the next one. It lives on the different things. So this R sharp modulo C R sharp, it's isomorphic to OK modulo C of OK. So if you take cross, of course, then you have a character chi. So this y chi essentially is the same thing. It's a canonical point. So let y0. So for example, there's a y0 be the CM point represented. Let me say y sharp represented by h0 and 1, canonical one. Then this y sharp chi, the summation of chi inverse of sigma y sharp. The sigma is something, Galois group, hc of h, k. If you are careful, audience, immediately realize that this is not well defined. Because this has a character here. So in other words, it's not really right invariant and y chi. So it's not really a divisor. It's a divisor with a character. I mean, in other words, you can, if you really insist a divisor, you have to raise your Shimura curve in the higher level. So this is actually the divisor with a character. Chi, I write this chi here. Chi r. So in other words, usually if you have 1 point and the modular curve Shimura curve, you want to be invariant, and the compact subgroup you start with, but this is not. But anyway, this is a nice thing. So this is a quasi Hington point. The reason this is very nice, in a sense that this description is simpler. And this conductor C Hington points is easy to describe. It's a level n, but when you compute height, a lot of headache there. It's very difficult. But this one apparently much easy to handle. Okay, so what's going on is, so now you also, once you have this thing, you need to also need to compute the projection of this psi. The projection of this psi in the space of big phi, space of pi f is given by y chi sharp, or maybe I write f here to determine this is actually component y chi f sharp dot the canonical form f here. So it is indeed a new form, multiple new form. Okay, that is great. So we construct two forms. One is a new form, one is a quasi-new form. How can I do? So third step is very important. So this first step work on x naught of n, second step work on a Shimura curve. We get two different things. The third step, so we want to show that. So this is phi minus 2 to the g plus 1 d k over f. This is not big D. It's actually the order form. So I have to say what I mean the order form. Order form means that if you compute the Fourier coefficient, so make the sufficient many 1 there, all the Fourier coefficient vanishes. So let me try to understand. So you compute the Fourier coefficient as Fourier coefficient. Equals 0 if A is a prime over Dn. So there's no Fourier coefficient can compute unless you're doing something. So this is a classical, this is exactly the same situation, the order form. When you say one form is odd, if we cannot find the first Fourier coefficient. So what can I say? This is the order form. And then the multiplicity 1 argument will imply that the projection of this difference on pi f is also odd. Okay? This means that, what does it mean? This means that f prime 1/2 chi and 1 f sharp square times f sharp minus 2 to the g plus 1 divided by square root of d k of f y chi sharp f square times f is odd. Odd means that the first Fourier coefficient vanishes, right? So this means that I take first Fourier coefficient here. The first Fourier coefficient equals 1 is equal. So I call this, this is a given name, call this thing. This is a quasi Gross-Zagier. Well, this is not something we want to compute. And very important, I have to say that in my paper of Asia Journal, this term is missing. And it's Vata, he read my paper, he couldn't understand it, so trying to convince me there's something here. So I go back to check, it's really true that this term disappeared. So this is something in the Asia Journal. Then we work on, I mean, there's a, so we have something f sharp, f, and the y chi sharp, and y chi. So there's two different systems. This is the system we want. This system I can prove, right? How can I do? So I make a careful understanding between the this and this. they come to the following thing. The following thing is that, so there is a, this is a GZ, so this is 1/2 sharp is close to be true, is that there is C of chi times the product V divide C P chi V, I will explain, lambda V times L1 chi of F derivative will be the formula I want. Will be 2 to the G plus N, 2 to the G plus 1 times Y chi squared. So where, it's very, very important, where Y C chi is constant depend only on chi, nothing else. This P chi Vt is a rational function. C of t depends only on chi v. Well, so that's something I can get. Actually, I even don't know what this thing is. I know it's a rational function. So to prove the real Gross-Zagier, I need to evaluate this thing. So this is the Gross-Zagier semi-quasi, semi-demi Gross-Zagier. So what we need to show this thing actually is simple. So step 4, redo all the theory, prove the same formula, prove the formula, the Gross-Zagier formula for non-holomorphic forms. For forms of weight 2, 2, 0, 0, of course for central values. Well, so you will get exact same formula here, except that it's G plus N. Here it will be is evaluation periods instead of heights. Then you get exact something here. That's amazing. Then what I get, so you will end up the same thing, same formula, C of chi, P chi V, lambda V, V divided C, and L1 chi F equals to 2 to the G plus N times that I write down there's a Y chi and I have a period with F prime. F prime is a modular form and Shimura variety of Kn type square of F prime square. And the amazing thing is this thing is the same as before. So this one completely the same. Yes? No prime. Yeah, so I've just for central values. Yeah, so you prove everything for non-holomorphic form, but this time you only for special value. The thing is unknown stuff here and unknown stuff there is completely same because they come from same kernel function. Now something important. So this is this last step is not written down. So we will be in my misery conference this report. So now evaluate. Reevaluate the periods Y chi F prime for F to be Eisenstein series. Because this whole method works for Eisenstein series as well, then I'm Eisenstein series with the parameter, Eisenstein lot of parameter, the value 1 plus t square, the lambda here. So t is any real number. So then you end up with C of chi times this V of C psi chi V over this A lambda V depends on t here will be something as simple as you want, 1 over square root of d. So what that mean that, but now you can show that all these numbers are rationally independent. That means that this thing is true even before you take these values. So this means that C of chi equals 1 over square root of d, P of chi v equals 1. So this is the basic idea of the proof. So somehow you want to prove something for the cusp form, but the cusp form nobody knows how to touch it, how to evaluate it. Then you prove it for a non-holomorphic form, eventually move to Eisenstein series. Of course, to do that, you need to understand the spectrum, continuous spectrum, just contribution to everything. But that, unfortunately, is well done by many people. So Eisenstein series was used here not for the evaluation of some constant we don't know how to handle. Well, this one you can evaluate this one quite easily. I mean, this is just some numbers. Just some is a product e to the it, I guess, plus e to the negative it for v or pi v. This lambda v here is just is simply pi qv it plus qv negative it. You know this one, if you have a function for different v, this will be linearly, this will be algebraically independent for all t. Okay, so that is the basic idea of the proof. So now I come to, I just want to, I have another half hour, maybe it's 15 minutes enough to explain what is exactly the difficulty to do this thing. Well, I mean, the first step, of course, I mean this construction of theta. So we have to construct two things. One thing is the construction of this phi goes as follows. So basically, you have this chi. This chi will give you something theta of chi. This is a theta series associated to theta series of weight 1 and the level d with central character. Central character is given by, I mean the extension, so it's basically given by AF of K cross norm of a K cross. We know this is exactly the Galois group of K of F. So this character is isomorphic to positive negative 1. So this is basically this character. I give a name called omega. You got a theta series. Then what's going on is you can, this thing is essentially some linear combination. I mean, this, of course, you can have a write as the pi theta of chi of, I mean, then you can compute, let me write down. You can compute this thing very explicitly, theta chi times some Eisenstein series. PGR2, sorry. Of PGR2 of A. This is some Eisenstein series of P of F, G of F, some F gamma G. I'm sorry, too many F. Let's just give another name called H. So this H is certain function from G of A, GR2 of A to complex number such as that H A X 0B of this thing satisfies standard condition you want. A over B to the S to the power omega of B and H of G. This kind of integral, you put this thing inside, then you can unfold the integral to make this into PGR2 of F. On the other hand, you can take the Fourier expansion of F. Then you can make a further unfold. Make this PGR2 So what do? You unfold twice and fold once. Then you end up an integral something like the Whittaker function of f of g and the Whittaker function theta chi of g epsilon g and f of g, s of g. S is already there. So this is totally z of a, n of a, g of a. This epsilon is -1001. So this one gives you the local error function product, the local thing. Now you apply the formula, the exercise I gave in the morning for the best place. So what's going on is this thing, if you forget the whole thing is like that, this thing will give you the error function of f. This thing will give you error function of theta chi. Then the multiplication of them will give you the Rankin-Selberg convolution. So this will give you, suppose that, suppose V is nice. So f of g, f of k, for example, equal to L to S omega V. And this integration is totally unramified. Then this will give you the Rankin-Selberg convolution. I will not go to the detail of S chi V F by the exercise, by the first exercise. Because the integration of W A0, 0, 1 of F A to the S minus 1/2 equals of A is a function, 1 minus 1 here, sorry, is the error function S of F. On the other hand, theta W of theta chi of A0, 0, 1 of S d cross of A will give you S of chi. So you bring these both of them to that one. You apply the exercise I gave. You will get the Rank-Zebra convolution. So this is fun. V is nice, but V is not nice. So you don't know. You can't get it directly. So what you can get is a linear combination. If V is not nice, then what do? You need to get a linear combination of several ones, of W theta I or W E I. And both of them lives in the representation space pi of this radical chi. And this is the representation space of pi of the character S minus 1 half, half of 1 minus 1 S, and omega. Then, if we do this, we will give you the Rank-Zebra convolution, the full of S chi F. So, I mean, the computation, you have to figure out which one is, which one is not. So, in summary, what I'm trying to say is that the theta kernel, I can, so in summary, so what do we obtain? We obtain a function theta. The F theta will give you Ls chi F. The theta is in the space the linear combination of some theta series times the Eisenstein series. If you study the Fourier coefficient of theta is made of the following thing. The following local thing. I write W V. I give a Kc, and I just write this stuff Kc and S. Of course, then G. So, what's this saying? This is a linear combination of the V. If I run that way, the theta I, here I will use. What's going on is if you have two functions, you compute the Fourier expansion of a product of them. So, the nth coefficient will be the product. One's m, one's n. You have to combine them together. So this will be. So this is the first. This is the Whittaker function Fourier coefficient with respect to some character psi of Fv. This will be linear combination of the same thing there, Wv of theta I of G. I write the eta here times 1 plus Kc here times Ei times Kc I here of G. So why would I write that here? This is with respect to the character psi x times Kc. This is with respect to the character psi 1 minus Kc of x. So that both of them are Fourier coefficients. With different characters, then the multiplication will give you this character. Okay. And the beautiful thing about this makeup is the following local function equation. I never seen this before. This the Wv of S, Sg equals omega v c 1 minus c times the epsilon facts. We know the global epsilon facts times omega v c 2 minus s of g. So this one is really a functional equation of the global one except this fact. I mean, actually, we can reprove the functional equation just working on this local, purely local thing. So let me just recall that what we make up is it looks like we start with the representation chi v and the representation of this small thing. We make up something, some kind of Whittaker function like that. And this cosine is a very nice parameter. What? Epsilon v. So this is a very important thing. Now on the geometry side. So I want the construction of height pairing. So what height pairing can give us? So with the same points, it's really the points I write down Tf, G of f of u. These are same points. So forget this thing. These are same points. So then I can take the Schwarz space of chi T of f, G of af. Then these will be same devices. Chi is same devices. So what this notation means? This notation means some function phi from this G of af of T of f to complex number such as that phi of t tx equals chi t. Let me write down this thing. Yeah, chi t of 5x for t is in T of f. So somehow you have a geometric space to work on for the same points. So one very nice thing to do is study generally. You don't want to height pairing for this one, the other one. You want to have more systematically. What do I mean? The height pairing between two same points. So what's going on is, so let m be a function on G of f by t invariant and then you will end up something. Then I can define the kernel function kxy will be summation m x gamma y inverse for all gamma of G of f. Let me try to understand what I do I write something make sense or not? No. Yeah. So let me try to understand what's going on. Let me rewrite the same points in a different way before I write down something. So this same point C will be TF, GAF. Now rewrite it as G of f. Of course, when I write it, I have a pairwise. I have a G of f. Take T of f. That's what I mean. Have G of AU, AF. Okay? So this is a function I start with. So I mean, I extend M2 to this whole thing. So G of f, T of f, dot G of AF. So then I can make such a function. So I can define, so the height pairing with the multiplicity function M is simply given by this kxy. So in other words, if I have two CM divisor, so if we have phi psi at both the CM divisor of the chi G of AF, T of AF, then I define the height pairing phi psi to be the integration phi kxy psi bar dx dy. The dx dy, a certain measure and CM divisors. Right, this one. This is one, the C or some whatever. This is C. CM points. Then somehow this thing, I mean the standard thing to decompose it. So now I do a lot of analysis here. So you can define it as a summation of the MKC or something called, there's a KC here. There's a KC belong to F. And this is the thing. But how can I compute this thing? Well, before I compute this thing, I need to understand the CM, how can I measure two different CM points? So in the morning, I talk about if you have one CM, the CM points can be, if you have two embedding, let's say phi 1, the phi B2, how can I measure the distance? The relative position of phi 1 and phi 2. Of course, I mean, if it is in the real plane, what do? You have a line here. It's one line. You have a second line. Now, of course, you have angle. You try to find a cosine, theta, or whatever. Find some angle. This angle is basically good Bayesian invariant. You measure them. In this case, it's something. What do? You fix one embedding. Then your B will be split. Say, when we fix this one, will be phi 1 of k plus phi 1 of k negative. Negative means that this one is itself. This one is anti-commutes with this one. Right? Now I pick up any B in K. Now my phi 2 of B will have B plus B minus, according to this decomposition. So for these two CM points, what I get is that, so I define phi 1 and phi 2, the relative position to be phi B negative divided by norm of B. And you easy to see this definition doesn't depend on the choice of B. And this gives you a canonic parameter for two different CM points. Basically, that's the invariant you get. Amazingly, this KC appeared here is is compatible with the KC I do for the Fourier expansion. So if we go back here, then you get the M of KC and certain the products a certain local number. And of course, if this one is a psi V there of KC. So this is local. This is the multiplicity. This is a local linking number. So we decompose the height pairing. So in other words, the cook of the matter in the height pairing also something appeared in the KC. So this local Gross-Zagier formula I will have to define that. Is that this W V of the KC 1/2 and 1 central value of G1 at the A001 here will be the linking number of T of A of a certain form locally. This is for CM points at KC. So this one is not that difficult to define. Just define to be G of FV, phi V k C, some gamma G, and per psi phi V. I mean, let me try to define what I really means. That if I have two functions phi per psi k C, it's really defined to be G of FV, the local thing, of phi of gamma G per psi bar of G dg. So this gamma is in B, is trace free, and the k C of gamma, as I just defined, equal to B minus divided by norm of B is equal to k C. So apparently, so this is a Gross-Zagier. What's the Gross-Zagier exactly mean that the Fourier expansion appeared in the kernel function, or in other words, the Whittaker function make up by the Whittaker function of the pi of f tensor with pi of chi, and sorry, there's a chi here, and Eisenstein series here. This thing actually you can purely, this is a local thing. This thing is purely local. You don't need to go back to global center at all. You can make up arbitrary function from here. The function this side will appear the function other side as well. This is one of course is enough to prove the Gross-Zagier formula for the central value. For derivative, it's very, very important. This MKC has a singularity if you take, so if you have the KC, you have one CM point here, another CM point here, the angle is KC, then here you have the singularity. This singularity is log of KC, something like that. Then you make a comparison. So this is the local, the comparison. And this is the singularity. Of this is exactly the singularity of the intersection. If you apply these two things, then you end up the proof of the Gross-Zagier formula. So in the summary, basically, the whole proof you are working on two different words. One is a word, is a geometric word. One is the analytical word. So this side, so basically, you have two groups you work on. So basically, in this side, you work on Whittaker functions. You start with, you have two representations to work on. You have pi of f, tensor with is pi of what? Of this pi of sigma, the chi character, and this Eisenstein series. And basically you work on the group of a triangular matrix inside the full matrix. So this is the word you work on. On the other hand, the geometric side, pairing, you work on totally different thing. You work on the torus T inside B. And amazingly, what I said that the B, the double coset, is parameterized by F. And on this side, this makeup is also parameterized by F. So this is why they can, it's a common parameter, they're giving this psi and F to make a connection between them. And I must say that even up to now, I still don't know philosophically why everything is true. Even I can reduce the proof of Gross-Zagier formula to the purely the purely local representations, but still don't know why these two words have so lot of things connect each other. Okay, maybe I should stop here.